Hello and welcome to another video, this time on a second order differential equation question sent to me by Daniela. And it's a good question. It's not easy. And it brings up something which they do all the time in exams. I think students often feel like they've got to derive the particular integral by, taking a guess at what the PI is likely to look like, differentiating it, differentiating again, and find the values of lambda and mu. That's not always the case. In fact, more often than not, they give you the particular integral, and all you've got to do is plug it in to the differential equation to establish, well, this result, for example. Anyway, let's get on with this. Complementary function. I hope you're familiar with that phrase. I often use it, but the book tends to use auxiliary equation as the phrase for the complementary function in Edexcel. But it's just simply the solution to when your second order equation, a differential equation, is homogeneous, i.e. equals 0. Yeah. So we're going to have m squared plus 1 equals 0. So m is plus or minus I, and therefore this is y equals a cos x plus b sin x in this case, yeah? And that's just because we're putting 1 in front of x there and there, and the real part of this would be like e to the px, but that'd be e to the 0, and so you end up with just that. Okay, so nice little start there. Now in part 2, we're told that this is our pi, yeah? So if you're told that it's the pi, well, it makes sense to differentiate it, find dy by dx, differentiate again, find the second derivative, and plug it into this, because it's supposed to solve this equation for all values of x, yeah? Okay, so that's what I'm going to do, and it's a bit of an algebraic grind, this. So we've got y equals p sine x ln sine x, if you like, or ln sine x sine x. It's a bit of an ugly function, but it is the general, it is a particular integral though, that's for sure. Okay, so we've got this, and we're going to do dy by dx first. Well, we're going to need product and chain rule. Firstly, I said p, and then I was like, okay, differentiate this, you're going to get differentiate within the function cos x times by 1 over sine x, so that's cos x over sine x. But then we're timesing that by sine x, the other side undifferentiated, and that's going to cancel. Plus, differentiate this part of the function, that's cos x, times it by that undifferentiated, so you're going to get cos x ln sine x. Plus q times, okay, same thing basically, differentiate x, you get 1, times it by cos x, undifferentiated, then differentiate cos x, you're going to get minus sine x, and then times it by x, so you're going to get minus x sine x. Cool. And that is the first derivative for this function. Okay, so now we're going to have to differentiate it again. Might help to just quickly write it down slightly neater. So what have we got? P cos x plus cos x ln sine x. Might even be wise to factorise out the cos x there. I might do that. So let's call this P cos x multiplied by 1 plus ln sine x. Try and make things easier for you if you see an easy win in the algebra. Plus q times by cos x minus x sine x. Okay, so now I'm going to differentiate again. Okay, differentiate this side, I'm going to get minus p sine x, times it by this side undifferentiated, plus differentiate this side, well, 1 differentiates to 0, and ln sine x is going to differentiate to cos x over sine x again, times by p cos x. Plus q times, remember, just ignore a constant because it's just a constant of differentiation. It doesn't do anything, it just sits about. Cos differentiates to minus sine, and then here we're going to get, well, sine differentiates to cos, times it by minus x, so you're going to get minus x cos x, but then you're going to differentiate to minus x, which goes to minus 1 times by sine x, so you're going to get minus sine x here. Cool. Okay, let's tidy this up a little bit. We've got minus p sine x, 1 plus ln sine x, plus p cos squared x over sine x, and then plus q times by minus 2 sine x minus x cos x. And now what I can do is I can plug in my y and my d2y by dx squared into the differential equation because it should solve it for all values of x, yeah? So plug pi in. And what are we going to have? We're going to have all of this, so I'm going to write it down, minus p sine x, 1 plus ln sine x, plus p cos squared x over sine x, plus q times by that. Was it plus y, d2y by dx squared plus y? I think it was. Yeah, and it equals 1 over sine x. So let's plug in this now, plus p ln sine x, plus qx cos x, and it equals 1 over sine x. Yeah, and I've got to try and show that this result is true. So that's what I'm going to try and do. So I'm going to times the sine x across. That's going to give me minus p sine squared x, 1 plus ln sine x, plus p cos squared x, plus q times by, I'll times the sine x into there, minus 2 sine squared x, minus x sine x cos x, plus p ln sine x sine squared x, plus qx sine x cos x equals 1. So a bit of a mammoth one, this one. Algebraic stresses. Now, this should all simplify. Let's have a look why it does indeed simplify. Firstly, that's going to disappear with that one because you've got a minus qx sine x cos x plus qx sine x cos x. So there you go. What else goes? We've got a minus p squared ln sine x, and then we've got a plus p sine squared x ln sine x. That is going to disappear. When you do that times that, it's going to disappear with this one. Yeah? What are you left with? We're left with minus p sine squared. Let's write it down. Minus p sine squared plus p cos squared. We've also got a minus 2q sine squared x, and then what else am I missing here? Yeah, minus 2q sine squared x, and that seems to equal 1. Now what are we heading towards? What are we trying to end up with? We're trying to end up with something which only has sine involved, so let's try and get just sine involved. Okay, if I write cos squared x as 1 minus sine squared x, so let's see if that does the trick. Well, we end up with a p at the start, which is good because I think that's what we wanted. And then we're going to have minus p sine squared x minus p sine squared x. Well, that's minus 2p sine squared x minus 2q sine squared x equals 1. Now, is that going to factorise nicely to give us, let's just check the format of the answer, minus 2 times p plus q sine squared. I think that's right, isn't it? Minus 2 p plus q sine squared x, because if I multiplied that out, it would give us the line above it, so it would give me minus 2p sine squared x minus 2q sine squared x. Perfect. So we've deduced it, yeah, as required. Now, the last couple of bits of this question. You just need to recognise that this is an identity. Look, they've even given you a massive hint in the question and written it as an identity. It should be an identity because this is supposed to solve this for all values of x, like just as this solves the complementary, where the equation equals 0 for all values of x, yeah? So this is supposed to hold true for all values of x. And now, whenever you've got an expression in maths which holds true for all values of x, you can use equating coefficients. So for part 2, you can just say, by inspection, p must equal 1. Yeah, because this is always true for all values of x. Well, this is always going to have a sine squared x on the left hand side. There's no sine squared x's on the right hand side, and so we can deduce that this term independent of the sine squared must be the same as this one, and so p equals 1. And if p was 1, how am I going to make this term disappear? Q equals minus 1. Yeah, and that will completely make the equation true, won't it? For any value of x, that will always be true. And so that's why you can make that deduction there. It's quite subtle. I agree, it's quite subtle. And then part 3. Well, in part 3, let's write down our solution. A solution is going to be CF plus PI, and so it's going to be this one plus that one, yeah, because that's a CF, that's a PI. So I'm just going to have y equals a sine x plus b cos x, whichever way around you want to write those two, plus, and now I'm going to plug in my p and q, ln sine x minus x cos x. Okay, that's the general solution written down. And it then says, state the values of x for which the solution is valid, justifying your answer. Well, you know, you can't learn a negative number, yeah? And that's why sine x must be greater than 0, yeah? Sine x must be greater than 0. You can't learn 0 either. And if sine x is greater than 0, just consider a sine curve for a minute. Where is sine x greater than 0? Well, between 0 and pi, not including 0 and pi. Hence, 0 is less than or equal to x is less than or equal to pi. And to justify that, because ln sine x is undefined when sine x is less than or equal to 0. Yeah? That's basically the answer. I noted in the mark scheme, though, they would have given you a mark if you'd looked at cosec x and said, well, that's going to have problems at 0 pi and 2 pi, and they would have given you 1 mark for that. They're always difficult ones where you've got to decide where the range, where the domain and range cause problems. They're always difficult. You have to think about it very carefully, and sometimes it's easy to miss a situation. But here, it's the natural logarithm which is causing the problems. Okay, hope that makes sense, Danielle. Keep up the hard work. Great question, difficult question, so I enjoyed doing that. And yeah, let me know if you get stuck on anything else. All the best. Bye-bye.